949. So from here, we calculate our stress average, which is 95.36 times 10 to the power 6, plus by 0 divided by 2. 95.36 power 6 divided by 2. 47.68. And then we find our tau max will be equal to square root of 47.68 times 10 to the power 6 squared plus by 949 times 10 to the power 6 squared. So 47.68 power 6 squared plus by 19.949 power 6 squared, square root of the whole thing is equal to 51.685 times 10 to the power 6 Pascal. Power 6 squared plus by 19.949 power 6 squared, square root 59.6. So these two steps that I've done is exactly the same as the previous two steps over here that I highlighted in yellow. Okay, so these steps, they're exactly the same. So from here, stress max is equal to 47.68 times 10 to the power 6 plus by 51.685 times 10 to the power 6. So 47.68 power 6 plus 51.685 power 6 is equal to 99.365 times 10 to the power 6 Pascal. Okay. So now we have the three location stress max, combined normal stress and shearing stress. So you pick stress max is going to be at where? It's going to be 143.04 times 10 to the power 6 Pascal. And it's going to be at x is equal to 2.4 meters. Okay. So we are going to design based on the stress situation at x is equal to 2.4, because at that position, you have your maximum principal stress, okay, which is your stress max. So now you can use this value over here, go to the materials handbook and select your material, okay, where you combine the shear force and bending moment. Okay, so I do understand that where I teach now, okay, so if you look at on Friday, right, forming the equation and drawing the diagrams, you guys have learned in 2PO4 before, okay, but combining them, analyzing the stresses and combining mole circle, which is what we have not done before, so this is new, and selecting the right position, okay. I did not know which position to choose. Oh, sorry, I did not know where the maximum stress will occur. We will only know that fracture will occur at the interface of the what? Flange and the web. Okay. Where was 143.04? Wait, did I make a mistake again? 143.04 is over here. Okay, it's the previous location where x is equal to 2.4, Arisa. Okay. Okay. Right. Wait, I got another question. Yeah, why is it the max? Is because This value is less than 143.04, and this value is 70.317. So it's a maximum. Okay, it's the biggest of the biggest. Okay, okay. The other ones are the maximum at their specific location. Okay, right. So now I'm going to go back to the shaft design. And we're going to go back to the shaft design. And I feel that this is somehow important to explain. Okay, so we are going back to shaft design. And I realized that I forgot to do that. Okay, back to shaft design. In shaft design, the shear force, okay, the shear force was what? Was ignored, right? We deliberately ignore the shear force, and I being obedient. Okay, I have to tell you that. Okay, okay, I'm being obedient. Okay, and I want to like show you. Okay, is this true? Because I did not know. Okay, I also like this is the first time I'm going to calculate this. I did not know. I just read the textbook and they say ignore it because it's low. It's not going to affect your principal stress. Okay, if I read, I'm going to tell you, and this is wrong. Okay, you don't just read and take it for granted. I think it's good to test it out. Okay, and I'm so scared now. What if we test it out and it is proven that the shear force is important? What are we going to do? Okay. So yeah, here we go. Okay, so we have selected. We have selected or we have calculated. If you have to look at last week, that our minimum diameter of shaft is what? So if we go back to week 11, Friday, we have selected a minimum diameter of 51.71. Can you see that? Yeah, that's based on our calculation. So we are going to is 51.71 millimeter. Okay. I'm going to, for calculation's sake, I'm going to use 52 millimeters. 51.71 is very hard to manufacture. Okay. I'm going to select. Then we are going to go back and look at some values. Okay. We are going to go back, and I need a pen now. Yeah. So we are going to go back to our analysis, right? To find out what is our V. Okay. So in terms of Vy, the maximum, I'm sorry, Vz. Okay, Vz is going to the page. The maximum value was 6632. Okay. And in terms of Vy, the maximum value is 3730. Okay, so we got that. So we got our Vy and we got our Vz. Okay. And then the maximum torque that we can see, right, is we calculated the maximum torque that we can see is 596.831. Okay. And then we have to know our moment. Our moment in Z is equal to 359? No, it's 559.5 or 55, yeah, it's 559.2. Okay, 559.2, 559. Okay, I'm going to take 559.5 Newton meter. And our moment in Y, our maximum moment in Y, okay, our maximum moment in Y is 1243.4. Okay. And they are at the different location. Okay, but let's deal with our shearing stress first. Okay, let's deal with our shearing stress first. So we know that Vy is equal to 3730 Newton meter. We know that Vz is equal to 6632 Newton meter. And we know that they are acting in the different location, right? 6632 is not in the same position as the 3730. So we only will use the higher value, okay? And we know the torque in the x direction, the maximum is at 596.831 Newton. So the other one is only Newton. I apologize. So we are going to calculate the shear stress due to Vz equal to 6632 Newton. Okay. So the shear stress is equal to Vz over Iyy Qy divided by T. Okay. So there are a bit of variables that we need to know. So we're going to find Qy first is equal to A y bar. So the area we're going to look at is half the circle, right? So it's equal to pi r squared divided by 2. The y bar, the centroid of the y bar, which I brought the exam, is 4r over 3 pi. Okay, so this is your A, this is your y bar, and this is from the formula sheet. Okay. So when you get rid of this, 2, get rid of the pi, get rid of pi. So you will have 2 over 3 r cubed. Okay. So that is your first moment of area. So we're going to calculate 2 over 3 r cubed. Okay. So r is 26 times 10 to the power minus 3 cubed. Okay. So 26 power minus 3 power 3 times by 2/3 is equal to 11717 or 11.717 times 10 to the power minus 6 meter cubed. Okay. So that is our first moment of area. Our I is equal to pi r4 over 4. So we have our pi, our radius is 26 times 10 to the power minus 3 or 4 divided by 4. So 26 power minus 3 power 4 times by shift pi divided by 4 is equal to 358.908 times 10 to the power minus 9 meter to the power 4. And we know that J is equal to twice of I, okay, times 2 is equal to 717 0.816 times 10 to the power minus 9 meter to the power 4. Okay. So I can quickly calculate our shear stress. So our VZ is 6632. Our QY is 11.717. Our IYY is 358.908 times 10 to the power minus 9. Our thickness is 52. So the shear stress is equal to 4.163 or 164 times 10 to the power 6 Pascal. And then due to torque, TR over J quickly, 596.831, multiplied by the radius, which is 26 times 10 to the power minus 3, divided by J, okay, is 717.816 times 10 to the power minus 9. So this is TR over J, okay. 596.83 times 26 power minus 3 divided by 717.816 power minus 9 is equal to 21.618 times 10 to the power 6 Pascal. All I can say now is, holy shit, it's not really small, is it? Where we stand now, okay? Because later on, we are still going to calculate the what? The maximum stress based on this value, okay? I will continue again on Wednesday. So when we combine them, like how we do our what? Beam bending, yes or no? You realize that the shear stress is very small. Maybe the normal stress is going to be really big. I don't know, okay? So it's good to prove the concept written by the textbook to see for ourselves. I'll see you again on Wednesday.